When a neural network relies on random initial parameters, the output is pure chaos. It confidently misinterprets its environment, failing at recognizing the simple shape. Early attempts to process images hit a computational wall. A tiny 100 by 100 pixel grid required 10,000 individual weights for just a single neuron. Forcing data straight through this tangled web created unstable math. Gradients, the mathematical signals that guide learning, would either shrink to zero or explode to infinity. The system made mistakes, but lacked the capacity to learn from them. This formula calculates a network's cost, or loss. By using functions like mean squared error, researchers figured out how to compress a massive system failure into a single calculable number. This 3D wireframe plot visualizes calculations as physical topography, creating a landscape of peaks and valleys. Think of the model state as a marble on a hill down into the deepest valley, representing the lowest possible error. Feeding data forward only proved where the marble started. To reach that zero-error valley, the network needed an architectural strategy to send its failures backward. In mathematics, the gradient points toward the steepest possible incline, so the network evaluates that gradient and steps in the exact opposite direction. Doing this once is easy, but deep learning requires calculating these partial derivatives for millions of individual parameters all at the same time. The solution is an algorithm called backpropagation. It uses the chain rule from calculus to compute these gradients layer by layer, skipping the redundant calculations that previously paralyzed networks. This computation graph charts out a network's math. Information travels in a forward pass, moving left to right, combining inputs to produce a final loss value. Backpropagation runs this in reverse. It computes the gradient starting at the final output and aerates backward to the original inputs. As error data travels upstream, it isolates each weight, dictating exactly how to adjust it. This backward pass allows the network to calculate the precise numerical update each individual parameter needs. By using its own failures to refine its foundations, the model evolves into a highly efficient, self-correcting system. Yet, an obstacle remained. Feeding high-resolution images into fully connected networks overwhelmed the computer hardware, because every single pixel still demanded its own individual weight. To bypass this bottleneck, computer scientists modeled new architectures after the overlapping receptive fields of the animal visual cortex, creating convolutional neural networks. Instead of wiring every single input to a neuron, CNNs use local connectivity. By sliding a small filter, or kernel, across the image, the network extracts local features using shared weights. This structural tweak collapsed the mathematical burden. A localized tile that previously required 10,000 separate weights now ran on just 25. With parameters minimized, gradients stayed stable during backpropagation. Neural networks could now stack deep layers and process massive, real-world datasets without stalling. These combined mechanics triggered rapid expansion. Deep neural networks quickly conquered highly complex tasks, like mastering general game playing. Global finance implemented the same optimized architectures to execute complex time series forecasting and identify subtle patterns in fraud detection. In diagnostic medicine, these convolutional layers identify microcalcifications, structural anomalies that were previously difficult for automated systems to isolate from high-resolution scans. While today's large language models and robotics rely on newer architectural shifts, like attention mechanisms, these still use this exact mathematical engine. Backpropagation is the core method used to navigate toward lower loss. Training a model via empirical risk minimization lays out a clear operational strategy. A highly effective system doesn't rely on making perfect predictions on its first attempt. It measures exactly how far off it is, calculates the direction of the error, and steps with absolute precision in the opposite direction.